Thank you guys all for coming, and welcome to our talk. It's called Isolation or Hallucination, Hacking AI Infrastructure Providers for Fun and Weights. Now, in this talk, we're going to tell the story of a little research project we've been doing these past couple of months. It started out with this little eureka moment, this discovery we had that we thought could affect lots of different AI companies as a whole. And it ended up with, again, myself being able to hack into some of the world's largest AI infrastructure providers, gaining access to millions of private models, data sets, prompts, and much more. So we're going to tell you all about that. But just before we do, quick introduction. So my name is Eli Ben Sasson. Here with me on stage is Sagit Sadiq. Both of us came here from Tel Aviv, Israel, which was an excruciating flight. And both of us work as security researchers at the Wiz research team, which means most of our day-to-day work is mostly cloud security-related research, platforms like Azure, AWS, GCP, et cetera. So we don't really come from an AI background necessarily, but I think it gave us a nice sort of outsider perspective. So this is what we're going to talk about today. We're going to start out by doing a little bit of AI 101, some basic terminology, and go over the discoveries that led to this research, how this whole research even began. Then we're going to dive straight into our 3 real-life case studies for today, which is how we hacked Hugging Face using a malicious model file, how we hacked Replicate using a malicious model container, and finally, how we hacked SAP using a malicious training procedure. Then we're going to sum things up and send you on your way with some takeaways on how to secure AI environments. All right, so first thing first, let's kick things off a little bit of AI 101, quick recap of basic AI terminology. And if at any point during this section the words I'm saying kind of sound like gibberish to you, then don't worry, because up until very recently they sounded like gibberish to me too. So starting things off with probably the most talked about AI term, which is the AI model. A model is basically a program, an algorithm that has been trained to make predictions or decisions based on the input data that you feed to it. All of us are probably familiar at this point with text-based models like ChatGPT and image-based models like DALL-E, where you feed some sort of textual prompt and get a response from the model. Now, in order to make the model do that, you first have to train it. And when we say training, we're talking about the process where you quote-unquote teach a model how to recognize patterns and make predictions based on those patterns. The way we do that is by basically feeding tons of data into the model. That's called a data set, and then adjusting its parameters accordingly. And finally, when you have the trained model you want to interact with it, that process will be called inference, which is when you apply a model that's already trained to new input and make it make predictions or decisions based on the input data. When you go on ChatGPT and ask it something ridiculous, and then it responds, that process will be called inference. So quick recap, you have an AI model. First, you have to train it, and then you can infer with it. But how do you actually do all those things? Because all those things are really expensive to compute, and not everyone has a GPU farm in their backyard they can use whenever they want. But luckily, there exist AI as a service providers, or AIaaS. So AI as a service providers are any one of those companies behind me and many more, which are companies that have very vast computational resources, and they basically allow you to rent them out. You can take your own AI model and run it using those companies' infrastructure, which is very convenient and also extremely expensive. So that was it for basic terminology. And now that we realize what AI models are, let's talk about what AI models really are. Because we realize that there are these complex systems, complex programs, but how does an AI model actually look like in real life? So at the end of the day, an AI model, like most things, is just a file or a couple of files. And the way that an AI model can be stored is using one of many different competing formats. There isn't like one standard way to save an AI model. However, there is one format that is by far the most popular, which is the Python pickle. So veteran hackers might be already familiar with the Python pickle. But even if you've never heard of this format before, you might want to check out the official documentation for it, right? So this is the way the official documentation for Python pickle looks like. And there's a really subtle detail in the screenshot. It's like a blink and you miss it type thing. But eagle-eyed viewers might be able to notice this giant red box in the middle of the page saying that the pickle model is insecure, that you should never open untrusted pickles, and that it's possible to construct malicious pickles that execute arbitrary code. So at this point, you're probably thinking, OK, but you just said that there's tons of different formats. This is the one insecure format, but the rest of them are probably much better, right? So not exactly. While the PyTorch framework produces those pickles I just talked about, another very big framework called TensorFlow produces models that can include lambda layers, which is a fancy name for arbitrary Python functions, which will be executed when the model is open. Other popular formats include the COG format, which is basically just a Docker container, and the Llama file made by Mozilla, which is literally just an executable file. So you get my point. AI models run code, or at least a lot of them do. But why exactly is that interesting? Because up until now, I didn't really reinvent the wheel here. Those are known problems. Some of them literally appear in official documentations. But the reason that we thought this was interesting, at this point, I think that most AI users know to not run untrusted models in their infrastructure. But what we thought was, wait, what about AI as a service providers? We just said that there's a huge market from small startups to huge corporates to everything in between. And their entire business model is that they're letting you run your own AI models on their infrastructure. So do all these companies realize that they're basically letting you run your own arbitrary code on their platform? And do they secure these services properly? So we went on a little mission in order to find this out. And the way we like to find things out is by researching around. So we researched around on some popular AI providers, and the stuff we found was actually quite shocking. We were able to get access to literally millions of private AI models, datasets, source code, secrets, logs, prompts, predictions, and the ability to interfere with all this data. And at this point, it should probably be mentioned that these confidential AI artifacts are often the unique intellectual property that differentiates a company from all its competitors. And a well-trained model or a very good data set could literally go for millions of dollars. So this is definitely confidential data that we should not have been able to access. So without further ado, I'd like to invite to the stage my good friend and colleague, Sagit Sadiq, in order to talk to you about our first case study of the day, which is how we hacked Hugging Face.
All right. Thanks, Eli. So let's get started with our first case study of the day, which is how we hacked Hugging Face using a malicious model file. So for anyone who's not familiar with the Hugging Face platform, this is what it looks like. And you can essentially think about Hugging Face as the equivalent of GitHub, but just for AI. This means that any user or company can actually upload their models, their datasets, or their source code into the platform in order to either showcase it to the community or to enable collaborations for these projects. Now, one of the nice features, nice convenient features in Hugging Face is that they actually let you test out models without requiring any setup from your end. So here in this picture, you can see me interacting with the Mistral model right in the Hugging Face platform. And all of the infrastructure required for this inference is actually being provided by Hugging Face. The model is actually running on Hugging Face backend. Now, the reason we thought this feature is very interesting because, as Eli said earlier, some model formats can actually result in remote code execution when being loaded. And I just said that literally anyone can register to Hugging Face, upload their model, and start interacting with it using the inference API. So does that mean that anyone can actually execute code on Hugging Face? Well, to test this theory out, we first have to craft our malicious model. Now, I know this process may sound a bit intimidating, but in practice, it was not too difficult. What we ended up doing was taking a legitimate model, specifically a pickle-based model, and then patching it using this short Python script in order to embed malicious functionalities within it. So when the model is loaded, it will actually execute our own quote-unquote malicious payload additionally. So we produced a malicious model, and we can now upload it to the Hugging Face platform. And now we can start interacting with it using the inference API feature of Hugging Face. So here in this picture, you can see me asking the model a legitimate question, and that it is able to provide me with a legitimate response. However, when I address the model using the backdoor keyword and ask it to execute the Linux ID command, it actually complies, and the Linux ID command is being executed. And as you can see, we're running with root privileges on the underlying Linux machine. Now, I know some of you might be a bit skeptical, thinking that this is just the model hallucinating stuff and that the ID command was never run. So just to assure you, we also asked the model to execute a fully blown reverse shell to us, which obviously worked, and we can now execute any command that we want right on Hugging Face backend. So the question is, what's next? What can we actually do with this type of access? So we know that many companies actually use Hugging Face in order to store their private models and their private datasets and source code. And we were thinking whether this kind of access that we now have can be actually leveraged into interfering with other customers. Can we actually access their models or their datasets? So in order to figure that out, we first have to understand what type of infrastructure is it? Where exactly are we running? So the answer for this question is that we are actually being run within a pod within a managed Kubernetes cluster. Specifically, this is an AWS EKS cluster. Regarding privileges within the container, we are running as root, which is quite nice, always convenient. But regarding Kubernetes permissions, unfortunately, we only have a very limited service account, which is quite of a bummer, because if we had, I don't know, a cluster admin service account mounted to our pod, we could use that in order to laterally move within the cluster and interfere with other customers' payload. But unfortunately, in this case, we only have a very limited service account. So just to illustrate the current situation a bit better, we are executing code within our own pod, which is hosted on a Kubernetes node. And besides our pod, we can assume, we don't know this for sure, but we can assume that there are pods of other customers as well. And besides this node, there are multiple other nodes, all hosted on the same AWS EKS cluster. And essentially, our goal for this research is to be able to interfere with the pods of other customers. So as I said before, we really want a privileged Kubernetes service account. This would be the ideal way for us in order to laterally move within this cluster. And luckily for us, Eli and I actually come from a cloud security research background, and we are familiar with this very cool trick that have actually worked for us multiple times in the past, where if you are running within an AWS EKS cluster, which in this case we are, and your pod is accessible to the IMDS, to the instance metadata service, you could actually fetch the AWS credentials from the IMDS, then using the AWS API, transform them into a Kubernetes identity that has the node's role inside that cluster. And that identity is actually a very privileged identity within the Kubernetes cluster. Now, if you want to read more about this trick, we actually documented it in our blog about Hugging Face, so you should really check that one out. But if we'll summarize the whole attack from start to finish, it would look something like this. So we as attackers crafted a malicious model file, specifically a pickle model. Then we upload it to the Hugging Face inference service, which gave us remote code execution within their Kubernetes cluster. Then we use the IMDS trick that I just described in order to elevate our Kubernetes privileges, which gave us access to the Kubernetes secret store. And using the secrets that we found within the Kubernetes cluster, we were actually able to get access to all of the models, datasets, and source code that is hosted on the platform. Now, when I'm saying all of the models, datasets, and source code, I mean both the public AI assets and the private AI assets of Hugging Face customers. Now, in terms of responsible disclosure, of course that we reported all of the issues that we found to Hugging Face, and we ended up actually having an extensive collaboration with them in order to fix the issues that we found and to make their platform even more secure in the future. And this would also be a good point to mention that we never actually interfered with any Hugging Face customers' data, and that all of the tests that we actually performed were performed only on secondary account of ours, especially not to interfere with other customers. All right, so now that we are done with our first case study of the day, let's move to the next one, which is how we hacked Replicate using a malicious model container. So for anyone who's not familiar with the Replicate platform, this is what it looks like. And essentially, Replicate is a very popular AI as a service provider. They actually have more than 2 million registered users, which is quite a lot. And their offering is that they actually let you choose one of their existing models in their model gallery, or you can upload your own model. And they let you scale that model using their infrastructure, which they provide a very convenient HTTP API for. Now, in order to upload your model to Replicate, you first have to wrap it in something that is called a COG container. So this is a screenshot from the official GitHub page of the COG project. As you can see, COG is an open source tool that lets you package machine learning models into a production-ready container. Then this container can be actually deployed either to your own infrastructure or to Replicate. So we were reading this and thinking, does that mean that anyone can deploy a container to Replicate? Well, to test this, we first have to craft our malicious COG container, which was very easy. All we had to do was to initialize a new container using the COG init. Then we modified one of the Python files there that instead of loading the AI model, it will simply treat our prompt as a Linux command, execute it, and give us the results. And now that our malicious co-container is actually ready, we can push it to the replicate platform in order to interact with it using their platform. So our model is now available on replicate, and we can start interacting with it. So I use the id command once again as my prompt. And when I let the model run on a replicate infrastructure, you can see that once again, we are running as root, which is once again very convenient. And the question is, what's next? What can we do this time in order to actually interfere with replicate customers? Once again, we want to know where exactly are we running, what type of infrastructure is it? And the answer for this is that this time we are running within a managed Kubernetes cluster provided by either GCP or another cloud provider named CoreWeave, which really depends on what hardware did we choose for our model to run on. Now, regarding Linux privileges, we are running as root, which is nice. But regarding Kubernetes permissions, this time we don't even have access to the API server. This means that even if we did manage to find a way to escalate our privileges within that cluster, the Kubernetes API server is not even available to us. We would have nothing to do with that service account. Now, this means that we would need to find another way in order to pivot within that cluster. So we started doing some network recon, and at some point, we actually stumbled upon this very special network connection. So as you can see, I issued the netstat command, and we have an established connection to an internal host on port 6379. Now, the reason that I'm saying that this network connection is quite special is because although we can see it, meaning that it occurs within our network namespace, we cannot determine who is the parent process for this network connection, meaning that the parent process is actually running in a different PID namespace, in a different container. So luckily, we are running as root, and we have sufficient network capabilities in order to actually investigate this network connection using tools like TCP dump and Wireshark. And upon investigation, we actually concluded that this is plaintext Redis, and that this internal Redis database is actually being used as a queue for inference tasks. So whenever you go to the replicate platform and enter your prompts at the replicate platform, a new task will be added internally to that queue. And then a worker pod within the Kubernetes cluster will actually fetch that task, execute it, process it, and then insert the result back to the queue. So we thought that this is very interesting because maybe this internal Redis task queue is actually serving more customers and not only our account. Maybe it's shared among replicate customers. So we try to connect to it using the standard Redis CLI, but unfortunately, we get an error saying that authentication is required and that we need to provide a username and a password in order to authenticate. But do we need to provide a username and a password? I mean, we already have a pre-established authenticated connection in a neighbor container. And we know that this connection is actually authenticated because we can see queries in the network capture. So the question is, what can we do in order to take advantage of the current situation and abuse the fact that our neighbor container has an already established and authenticated connection to that database? So just to illustrate the current situation a bit better, we are running code within our own container, which is hosted on a Kubernetes pod. And besides our container, there is a different container. We assume that this is some sort of a management container that has an active connection to an internal Redis task queue. Now, the reason we can see this connection is because we are sharing the same network namespace with that management container. And upon investigation, we actually concluded that this connection is also plain text and pre-authenticated. So the way we leveraged our type of access in order to move laterally within that cluster is that we ended up injecting, using a TCP injection attack in order to hijack that authenticated connection and inject queries of ours to that Redis database. And what we ended up injecting is this very maliciously looking minified Lua script, which essentially proves that we can both read and modify all of the entries within that Redis database. And once we quote-unquote compromised this Redis database, we also concluded that other replicate customers use the same database as we initially suspected. So just to illustrate the whole attack from start to finish, it would look something like this. First, we crafted a malicious code container. Then we uploaded it to the replicate inference service, which gave us remote code execution within their Kubernetes cluster. Then we used the TCP injection attack in order to bypass authentication to the centralized Redis database, where we found all of the prompts and predictions, meaning the answers of the prompts, of replicate customers. And besides finding all of the prompts and predictions of replicate customers, we also noted that the data within that database is actually live data, meaning that if we were to interfere with the data, if we were to modify one of the entries, it would actually affect replicate customers in real time. And conveniently, the data that was found within that Redis database is actually for both public and private models hosted on that platform. So in terms of responsible disclosure, of course, that we reported all of the issues that we found to replicate, and we collaborated with them in order to fix the issues that we found. We actually had like quite a few of productive Zoom calls where we discussed what would be the best way in order to patch the issues that we found. And they ended up implementing what we call defense in depth in order to make sure that the issues that we found won't be able to be replicated in the future. And with that being said, I'd like now to reinvite Eli to talk to you about how we hacked SAP using a malicious training procedure.
Thank you, Sagi. OK, so after we talked about how we hack two platforms using malicious models, let's talk about how we hacked SAP using a malicious training procedure. So when we talk about SAP, we're probably thinking of the flagship product of SAP, the SAP ERP system. You're probably imagining all these like crazy dashboards with tons of graphs and charts and business data. But the truth is SAP today is actually much more than that. They're a modern cloud company with a large suite of cloud services and an AI service as well, which looks actually kind of the same. But this service, called SAP AI Core, allows for lots of actions with AI models. Not only does it allow to host AI models and AI applications like the previous two services, but it also allows you to train AI models, which looked very interesting to us. So how do you train an AI model on SAP? So the way that it works is actually quite simple. You provide one simple configuration file, and you're basically good to go. Your training procedure just runs. And the way the configuration file works is also quite simple. As you can see in the example here, you basically provide all the flags that you want to pass to the container, what sort of container image I want to use, what sort of flags I want to add, and most importantly, what command do I want to run within that container. In this particular example, it's a Python script, but it can be literally anything, including a reverse shell. So essentially, running code on SAP is not a bug. It's a feature. No vulnerability needed. So now that we run code on SAP, the question is, what's next? What exactly is happening? Where exactly are we running? And how can we exploit this new environment? So where are we running? Unsurprisingly, we're once again running on a Kubernetes cluster. This time, it's not a managed one. It's just an unmanaged Kubernetes cluster. So all the relevant tricks from before will not work here. Are we running as root? This time, we're not running as root. We're running as the nobody user, which is kind of a bummer. But maybe, finally, we'll have an interesting Kubernetes service account, interesting permissions that we can leverage in order to laterally move within the system. But this time, we don't even have any service account. So absolutely nothing in that direction. So we're looking at this sort of starting picture, and we realize that we're in a slightly worse starting position than the previous two researches. However, we do have one interesting advantage that we didn't have previously, which is that we can control the entire configuration of the pod we create. So let's add some interesting flags to the container and modify the environment to fit ourselves better. First order of business, run me as root, please. However, this does not work. I'm getting blocked, and I cannot change my UID to 0, which is the root user ID. But there are so many other interesting flags that I can add to the pod. I can try to make my container a privileged container. I can make a new network namespace, a new PID namespace, a new host disk, or anything of the sort. However, none of those things work. Every sort of interesting flag that I try to add gets immediately blocked by the admission controller, and the container won't even allow itself to run when I add interesting flags to it. So we're very limited with our compute, which is frustrating. But this is still Kubernetes. We have an internal network, which can contain many interesting things. So let's try to scan the internal network and find interesting stuff. But that also doesn't work, because every network request that we try to send gets immediately blocked by some sort of firewall, and we don't even get a response from the actual resource we're trying to access. So this seemed interesting to us. A firewall? What sort of firewall is it? So in reality, that wasn't exactly a firewall. It was a steal. which is a service mesh solution. It basically allows you to manage your Kubernetes service mesh network in a centralized way, blah, blah, blah. But in this case, it kind of acted like a firewall would. It stood between me and the traffic that I wanted to send, and I wanted to get rid of it. So how exactly does Istio work? And is there something interesting that I can do with it? So I did a little bit of Googling. I experimented with Istio, and apparently this is the way Istio works. It sets all these traffic rules. Those are called IP tables rules within your system, and you don't have to actually read them. They're actually quite simple. It says, take all the traffic going in and out, pass it through Istio first. Then Istio can decide what to do with it. However, there was one interesting stipulation that I just couldn't really believe my eyes when I saw it, which is take all the traffic coming in and out, except traffic from the user ID 1337. So I was looking at this, like scratching my head. Why exactly is the UID leet explicitly excluded from all the rules within this IP tables table? So I Googled, and apparently this is not an SAP thing. It's an Istio thing. 1337 is Istio's own user ID, and this is the way that Istio excludes itself from its rules. So I said, OK, this kind of makes sense, I guess, but if I can read this correctly, then the UID leet would be completely exempt from all the traffic rules here. And I know that I can't really set my UID to 0. I can't really be root. But maybe I can just set my UID to 1337 and see what happens. So this is exactly what I did. And this is how it worked. In my previous attempts, when my user ID was nobody, and I tried to access something within the internal network, I immediately got a bad gateway response from Istio. Istio basically said, you're blocked, and you can't access this resource. But once I changed my user ID to 1337 and tried the exact same request, I suddenly get a 200 OK, and I can do whatever I want. So I can now have unrestricted access to SAP's internal network just because I set my UID to leet. So amazing. I have unrestricted access to the network. Now what? What's the next move? So normally I would say, let's scan the network. Let's fire up Nmap, try to find all these interesting hosts and ports that we can check manually. However, this time, we have an amazing cheat code up our sleeve, which is Istio itself. Istio has all these rules of stuff that we shouldn't be able to access, that stuff that were explicitly blocked for us to see. Let's take a look at all of Istio's rules and see all the hosts and ports that we can check. So this is exactly what we did. We went by the list, and this is the stuff that we found. The first thing we found was a server called Loki. Loki is a log aggregation system made by Grafana, and this is basically the solution that SAP used in order to collect all the logs from the service. They stored all the logs using Loki. Now, Loki has a /config API, which is supposed to print out the full configuration of the server. So we tried accessing /config, and we saw the configuration. Within the configuration was something that we really didn't expect to see, which was a bunch of AWS secret access keys. And those secret access keys gave us access to Loki's S3 bucket. That S3 bucket contained a huge trove of internal SAP logs, both from SAP AI Core, the service, and from customers' own resources, meaning that those logs contained confidential customer data. So already off to a bad start. That was the first thing we found. The second thing we found was a bunch of EFS file shares. And if you're a pen tester or a red teamer, then definitely listen up on this one, because this trick has worked for us on countless different engagements since we did this. So an EFS file share is, EFS is basically a network-based storage service. It's made by AWS. And it's a really weird sort of beast, because on one hand, it's this modern managed cloud storage service, but on the other hand, it runs on the NFS protocol. That NFS protocol, the protocol invented in the 1980s that has barely changed anything since the 1980s, which leads to all sorts of vintage security problems. For example, an EFS share by default does not require any authentication in order to log in. You can, as long as you have network access, as long as you can see the actual share, you should be able to access it without needing to provide any sort of credentials. So we wanted to see, did SAP fall victim to the sort of insecure default? And the answer was yes. In those EFS shares, you can see that the command I'm running is nfsls. All I have to supply is the path. I don't have to do a username, a password, a token, or anything. Anyone within the internal network could have seen those shares without needing to do basically anything. And within those shares, we found a bunch of folders categorized by customer ID. And within each customer, there were a bunch of private model files, a bunch of private source code, and a bunch of data sets. So confidential AI data that was basically exposed within the network without any credentials on it. So those were the first two things we found, but the final thing we found was by far the most shocking. So let's talk about Taylor. Helm is a very popular package manager for Kubernetes, and up until version 2, it used to have a server component to it, which was called Tiller. Tiller was the server of Helm. Now, the way the server works, it has an API, a gRPC API, as Kubernetes loves to do. And once again, this API does not require any authentication by default. A little pattern for the services we found here. So we're once again wondering, can we actually try to access the server without any credentials, and maybe try to read some of the packages within that Tiller server? So this is what we did. We tried to read the package, and within the first package we actually found a bunch of credentials. So those credentials were to SAP's Docker container registries and to SAP's Artifactory server, which stores build artifacts. If you take a closer look here, you can see that the usernames are admin, admin at SAP, and admin2. So a very strong set of credentials, meaning that an attacker with the same level of access we had could not only have read the internal images, Docker images stored within the server, but also interfered with them, possibly planting malicious code into them and have that code executed on whoever uses those images. But this was only using the read command on Tiller. Tiller also has an install command. So I wanted to know, can we actually just install arbitrary Helm packages on this Kubernetes cluster? Short answer, yes. Long answer is that we crafted a malicious Helm package, which basically said, create a new pod, mount that pod with cluster admin credentials, and have that pod execute a reverse shell back to us. And once we got the reverse shell, we executed the kubectl cani command, which lists all the things that you can do within the cluster. This is the output of that command. It's actually a very corrupt screenshot. This is the full list of privileges we had within the Kubernetes cluster. So obviously a very strong set of credentials. With this access, we could have interfered with everything going on in SAP AI Core. We could have interfered with live training procedures, with live AI models getting run, with live AI applications. But this wasn't all, because at this point we got reminded that when we set up our SAP AI Core account, we got prompted to enter all sorts of cloud credentials for ourselves. When I needed to use S3 to store my files, I got prompted to enter my AWS credentials. When I wanted to use Data Lake, I had to input my HANA credentials. When I wanted to pull images, Docker images, I had to put my Docker Hub credentials. So we wanted to see, could an attacker with the same level of access we had gain access to all of those secrets? So we obviously tested this on our own accounts. We didn't want to actually access customer secrets. And the answer is yes, we were able to access all of those secrets in plain text. Here you can see, blurred obviously, but you can imagine, my own AWS secret access keys, my own Docker image pool secret, meaning basically an attacker with the same level of access we had could have gained access to all of SAP's customers' sort of Azure credentials, AWS credentials, Alibaba credentials, all the cloud credentials that were required in order to operate the service. And an attacker with the same level of access could basically not only interfere with SAP environments, but also spread from SAP to SAP's customers' environments independent of SAP. So a recap, kind of overwhelming, quick recap of this attack. We basically started with legitimate privileges, gaining legitimate access to the AI workflows engine, which all happened within a DMZ, a closed sort of network. And once we were able to escape from that DMZ using our Istio bypass, we gained access to the internal network. Within the internal network, we were able to find an exposed Loki instance, which exposed internal customer logs, a bunch of exposed DFS shares, which exposed private customers' models and datasets, and finally, an exposed Helm server that gave us admin access to SAP's Artifactory server, SAP's container registries, and full control over the Kubernetes cluster, which gave us wide access to customer credentials and customer data. So, quick recap. In terms of impact of this attack, we were able to access customers' models, datasets, source code, and internal logs. And on top of all of those AI artifacts, we were also able to access their cloud secrets. So, of course, all those issues were reported to SAP as soon as we found them, and we actually worked very closely with SAP security team in order to help fix the bugs. There was actually a couple of iterations of fixes that we did with them in order to make sure that this sort of attack can never be replicated again, at least not in the same way that we did. And of course, all the secrets that we have been able to access have been rotated since, so you don't have to worry about that. So these were our 3 case studies for today. Now let's sum things up with the takeaways that we learned and we want you to leave with here today on how to secure AI environments. So the first thing we want you to leave with here today is that AI models are code, or at least they often are. And they should be isolated accordingly, meaning that you should always properly separate between those external AI models and your internal sensitive infrastructure. That applies whether you're an AI company like those companies are, or you're just a company that uses external AI models. You should use stronger separations between those things like you would if it was an external program or an external library that you don't fully trust. An AI model should be treated the same. We would also recommend to use safer formats whenever possible, formats like safe tensors or GGUF. Obviously, no format is perfect, and you can always find vulnerabilities. But the sooner that we shift to those safer formats, the more secure that the industry becomes in the long run. The second thing that we wanted to find out here today, basically, is what exactly is the potential impact of hacking an AI service. Thankfully, we haven't really seen any actual adversarial attacks on these services. So we wanted to see how scary is this scenario. What sort of stuff can be achieved when people hack an AI service? And in our cases, we were able to access millions of private models from some of the world's largest AI companies, huge data sets, which can often include sensitive customer data, user prompts, codes, and cloud secrets. And we weren't only able to read all that stuff, but we were also able to actually overwrite it, to actually interfere with it, which means that we could have conducted supply chain attacks on AI researchers and developers who use those services, use those models in their day-to-day work. But it wasn't only limited to actual AI developers, but also to regular AI users, because we could have interfered with the actual AI pipeline, and whenever someone goes to their favorite LLM and types in some sensitive business question, we could not only have seen this question, but also return a malicious response instead, basically breaking the trust that users have in those AI services. And the final thing we want you to leave with here today is that AI security is also infrastructure security. Some of the bugs we found here today, not all, but some, are basically infrastructure bugs, which could have occurred in AI environments and in non-AI environments as well. So you should definitely pen test your internal environments, definitely collaborate with security researchers, and basically make sure that your environment is constantly challenged by good guys. So fingers crossed that you won't actually find anything, but if you do, we hope that it won't be access to all of your customers' private models. Thank you very much for listening. Thank you for having us. And if you guys have any questions, welcome to step up. You're also welcome to reach out to us on Twitter if you're interested in further questions. And yeah, thank you.